Hello, and welcome to ICMR NI's online course on causal inference from observational studies, NICER 201. In this session, I'll be talking to you about directed acyclic graphs. In my earlier session on epidemiological approaches to causal inference, I had discussed with you one of the models, which was the causal model or the causal graphs that illustrate essentially the qualitative assumptions about the causal relations among various variables and where we ascribe them as exposure and outcomes and covariates. We saw that these causal diagrams actually help us to recognize and avoid some of the common mistakes that we may do in terms of causal analysis, and it provides us with a united framework for evaluating both the design of studies as well as the analysis strategies for any causal question under a specific set of causal assumptions. We had looked at specifically the various components that make up a causal graph, the structure of the graph, the various connections, directed connections, undirected connections, the types of some kinds of paths between the variables, specific qualities of the variables on specific paths, such as some of the variables we call them as mediators, the ones that fall in between the path from the exposure to the outcome in the direction of the arrows. Then there were other variables which we called as colliders, which are again variables that fall in between the exposure and outcome, but here the two arrows actually collide onto that particular variable from the exposure and the outcome. In this session, we're going to look at specifically the directed acyclic graphs, and I'll be dividing this into two sessions. The first session we'll talk further about the structure specifically of directed acyclic graphs, and then in the second session I'll talk to you about some of the rules that apply in terms of that help us to make causal inferences and the assumptions that we draw from these graphs. So let us move on to the structure of the directed acyclic graphs. Directed acyclic graph is a causal graph where every edge is an arrow that represents the effect of the parent variable on the child or the affected variable, and no arrow comes back to its parent variable. That is, there are no feedback loops, and hence it's called as a directed acyclic graph. Causal directed acyclic graphs, or DAG for short, represents a complete causal structure in that all sources of dependence or associations are explained by the causal links between various variables. In particular, all the common or shared causes of variables in the graph are also shown in the graph. Here we have an example of a directed acyclic graph where the exposure is represented as E and the outcome as D, and we have 5 covariates: M, C, K, G, and P. Now, how would we read this graph? Based on the direction of the arrows that we have between the various variables, we can say that E leads to D, E leads to M, and M leads to D, E leads to K, and D also leads to K, C causes E, and C also causes D, G causes E, and G also causes K, K causes P, and P causes D. So let us now look at how we define the different kinds of path that we find in a DAG. Remember that a path is any trail that goes from the exposure to the outcome along on the arrows. These paths can be of two types. They can be causal paths or non-causal paths, and both causal as well as non-causal paths can be either in a state of being open or closed. In this example here, we have 6 paths: ED, EMD, ECD, EKD, EGKD, and EGKPD. Remember that a path is going from exposure to the outcome along the arrows, ignoring the direction of the arrows. Based on the direction of the arrows, we can then classify them into causal and non-causal. So of the 6 paths that we have in this causal diagram, all those paths in which all the arrows go in the same direction from the exposure to the outcome variable are called as causal paths. Hence, of the 6 paths, we have 2 of them can be labeled as causal paths, that is ED and EMD. The rest of them, EKD, ECD, EGKD, and EGKPD, are all termed as non-causal paths because at some point or the other, the path is going opposite to the direction of the arrow. Now, these, as I said earlier, these causal paths and non-causal paths can be either closed or open. We have seen one of the types of variables earlier known as a collider. A collider is a variable on which 2 arrows collide from any 2 variables. So here in our example, and this collider is designated based on the path. So here we have the path EKD, where the 2 arrows, one from E to K and D to K, collide with each other, right? So then K is a collider on the path EKD. We have another path which involves K, which is EGKD. Again, on this path, K with the common causes of K are G and D, right? And as you can see, the 2 arrows collide on K here. So again, K is a collider on the path EGKD. However, if look at the third path, which includes K as a variable, it is EGKPD. On this path, we do not have arrows coming from 2 sides towards K, right? K doesn't have parents. K only has one parent in this path, which is G, the EGKPD path. Hence, on this path, K is not a collider. Now, a path on which there is a collider will always be closed. And the paths where you do not find a collider would be the open paths. So, based on that, we can say that the 2 of our causal paths, ED and EMD, are open because you don't find the variable K as collider on these 2 paths. Among the non-causal paths, ECD is an open non-causal path, again because there is no collider on this path. And EGKPD is also an open but non-causal path because there is no collider on this path. We have 2 paths, EKD and EGKD, where K is a collider, and hence both of these paths are closed. So, be sufficient to say that all causal paths will always be open because they are in the direction of the arrow and there would never be a collider on a causal path. Whereas non-causal paths can be either open or closed depending on the presence of a collider. Another terminology or the kind of path that we need to remember is what is called as a backdoor path. Now, what constitutes a backdoor path? A backdoor path has to follow these 3 conditions. Number 1, it is not a causal path, and number 2, it goes from the exposure to the outcome, disregarding the direction of the arrow, and finally, and very importantly, this path does not start on an arrow pointing away from the exposure. So, in our example, we actually had 4 non-causal paths, if you remember. Right? We had ECD, EKD, EGKD, and EGKPD. Of these 4 non-causal paths, we have one of the paths, EKD, where it starts on the arrow pointing away from exposure E. So, we'll have to disregard that as well. And finally, we are left with 3 paths, ECD, EGKD, and EGKPD, and these are the 3 backdoor paths. one way to simplify identifying backdoor paths is actually to redraw your DAG by removing all the arrows that go out from E or go out from the exposure variable. And then this is how your DAG will look like. Now, all the paths that remain on this tag where we have removed all the arrows that go out from exposure variable E would be backdoor paths. So we have ECD, we have EGKD, and we have EGKBD. If you remember, we said that any path which has a collider on it would be a closed path. Otherwise, it would be an open path. Hence, if you see, we can now consider ECD as an open backdoor path because there's no collider on this path. Also, EGKD now would be a closed backdoor path because we have K as a collider here. However, the third path, EGKBD, would be an open backdoor path because here K does not act as a collider. So now we have seen the various types of paths. The paths can be causal and non-causal, and each one of these can be either open or closed. And we've also seen a special kind of paths, special kind of non-causal paths that are known as backdoor paths. In the next session, we will see the various rules that governs these paths and that those rules that will help us to make causal inferences between the exposure and the outcome. Thank you.